Hello, multivariable calculus students. This is Mr. Johnson, and this is section 9.7, which is on cylindrical and spherical coordinates. And this first video will be on just the cylindrical coordinates, which is almost a direct connection to polar coordinates from last year. So let me quickly remind you of polar coordinates. If you have this diagram drawn, you have cosine of the angle written as x divided by r, and you could convert that to x is equal to r cosine theta. If you do the same thing with sine of theta, you get y is equal to r sine of theta. And you could also do the Pythagorean theorem and get x squared plus y squared is equal to r squared. And last but not least, you could do the tangent of the angle equal to y over x. So here is the set of equations associated with polar coordinates that hopefully you remember from last year. And if not, this is your very quick refresher on that. Remember, when you have x and y coordinates, you go x units and y units to a point. And with polar coordinates, you take an angle from the positive x and you go r units out from the pole. Okay, so that's how we get to our polar coordinates. And what we're going to do with cylindrical coordinates is that we're basically going to simply add the z component. So if you move down here, you can see that with cylindrical coordinates, we are focused on symmetry about an axis, whether that's the z-axis or the x-axis or the y-axis. We want some sort of symmetry about a axis. So if you look at, for instance, here, the x-coordinate, the y-coordinate, the z-coordinate, you land on a point. Well, with cylindrical coordinates, what you have is the angle off of the positive x, that's identical to polar coordinates in single variable calculus. You go r units out from the pole, again, exactly the same as last year. And then all you do is go simply z units up. So really all we're doing is polar coordinates with the addition of the z component, making it cylindrical coordinates in space. You can see that all of the formulas still apply, but again, z is itself. So you don't have to do anything with z. Z is the same both in cylindrical coordinates and in Cartesian coordinates, and that makes this process relatively straightforward. So I think that cylindrical coordinates are not too bad. Remember, you have some sort of, well, cylinder, that's kind of part of the name. You have some sort of kind of circular motion about one of the axes. Okay, let's go on to the next page and try example 1. All right, so in example 1, we are going to attempt to plot the point and then convert coordinates. So let's say we have our z and our y and x coordinates, or axes, excuse me, and we're going to plot the point to 2/3 and 1. And remember from the previous page, this is r and theta and z. It's really important you keep track of that, especially with spherical coordinates, because it's easy to mix those things up. With spherical coordinates, we'll have a second angle, so keep in mind where everything is in the ordered pair or ordered triple, okay? So we have, I'm going to do the angle first. So we have an angle of 2 pi over 3, which is going to put us sort of right here-ish. So here's the angle right there. That's going to be 2 pi over 3. Then we have r, which is, of course, this distance right here. That's going to be 2. And then we have our last little bit, which is going to be 1 unit vertical along the z-axis. So that's going to be 1. And there's our new point right there. 2 pi over 3, and 1. Okay, now what we're going to do is convert this to rectangular or Cartesian coordinates. Again, we know that r is 2, theta is 2 pi over 3, and z is 1. So we have z. Z is all done. It's always 1 in this problem. We have x equal to r cosine theta, which means we have 2 times cosine of 2 pi over 3. And cosine of 2 pi over 3, be careful with this one. It is going to be negative 1/2. So we have negative 2 times 1/2, and that gives us negative 1. So that's going to be our x component. And then for y, we have r sine theta. So we have 2 times sine of 2 pi over 3. This one will be positive. Sine of 2 pi over 3 is root 3 over 2. And so we end up simplifying to the square root of 3. So our answer to part A, the rectangular coordinates for this particular point is -1, square root 3, and then z is, of course, still 1. That doesn't change. So there we go. That's going to be our answer for A. Okay, let's try B. So we're going to find the cylindrical coordinates for the point whose rectangular coordinates are 3, -3, and 7. So again, we have x, y, and z there. Okay, we can do this a couple different ways. I think the easiest way to handle this would be to first maybe do 3 squared plus -3 squared equal to r squared. Again, what we're using here is that formula for just the Pythagorean theorem from the previous page. So what we get is 18 equal to r squared, which means we have 3 root 2. So that's going to be our r value. Excuse me. Next, we're going to find our angle. So one of the things we could do is take the tangent of tangent of the angle equal to y over x, and that would give us tangent of our angle equal to y is -3 and x is 3, so we get tangent of the angle equal to -1. And this is where it can get a little bit tricky. Okay, so I'm thinking this is a 45 reference angle, 45-degree reference angle. So for instance, this is a 45-degree reference angle. However, both sine and cosine are positive. So that one's not going to work. We could go over here to 3 pi over 4. Now they're both negative. I'm sorry, one's negative and one's positive. The problem is, so in other words, tangent of 3 pi over 4 is -1. But the problem is that x in this quadrant is negative. However, in the problem it says x is positive and y is negative. So we also cannot have that particular angle either. Down here in the third quadrant, they are both negative, so that's not good. And so we could land over here at 7 pi over 4, where cosine is positive and sine is negative, and yet the tangent of the angle is -1. So we're happy there. So what I'm going to say is that my angle right now is 7 pi over 4. Okay, so our answer then is going to be 3 square root 2, 7 pi over 4, and then z never changed. It is -7. Now I'm going to offer just an additional answer to this one, just so you get the idea that there's actually a bunch of answers that are correct. Let's say that I want to name this angle -pi over 4. That's completely fine. So we could say that our point is 3 root 2 and -pi over 4, -7. That's completely fine. Let's throw a little bit of a wrench in this. We also could label our r value as negative. Now, what that does graphically is that it goes opposite the pole. What that means is that if you land at, let's say that we're landing at this, let's just take this angle, -pi over 4. So if we land at -pi over 4, but if our r value is -3 root 2, we actually go opposite the pole and we would land here, which is going to obviously be wrong because remember x is positive and y is negative. So what we could do is we could actually stop our angle at 3 pi over 4. So in other words, we go 3 pi over 4 like this on our angle, but then our r value is negative, which means we go opposite the pole and we land exactly where we want to land. And so you could have the black one right here. You could have that ordered pair as well as an answer. So there's an infinite number of answers based on that angle. Use whichever you like. Just keep it simple is my advice. Okay, let's move on to example 2. So we want to describe the surface whose equation in cylindrical coordinates is z equal to r. Now this is basically the goal to this is to tweak this and put this into an X, Y, and Z form. What we need to think about is how do we handle what is happening with R right there? R is obviously the portion that is in cylindrical coordinates. I mean, Z is part of it as well, but we can keep Z. We want to try to figure out how to swap out the R with the X's and Y's. And if you remember, one of our equations that we know is a connection between R and X and Y is R squared equal to X squared plus Y squared. So the question is, how could we possibly manipulate this problem in order to see that R squared show up? Well, what if we were to square both sides? What if we were to let Z squared equal R squared? And if that's the case, then Z squared is equal to X squared plus Y squared. And if you go back maybe 2 pages in your notes, you can see that grid that shows the different surfaces. And this is the kind of generic equation for a cone. I think that the generic equation is Z squared equal to C squared equal to, I think it's X squared over A squared plus Y squared over B squared. You can double check that in your notes, but that would be the general format for the equation of a cone, which is what we have in this type of situation. Okay, let's try example 3. So find an equation in cylindrical coordinates for the ellipsoid given by that equation. So this is the opposite of what we're doing in example 2. We're going to try to come up with an equation that is written solely in cylindrical coordinates, not rectangular or Cartesian coordinates. So I'm looking at that x squared plus y squared. I like most of that the way it is, although I need to kind of manipulate this 4 here. So I'm going to factor out a 4, and remember x squared plus y squared is equal to r squared, and we have successfully written our equation then in terms of cylindrical coordinates. You could solve for z squared, but it would not be necessary. Either one of these is totally fine. Okay, in the next video, we're going to talk about spherical coordinates. Thank you.